A quote from Michio Kaku: "We may have to rewrite all the textbooks on the beginning of the universe." It takes many billions of years to create a galaxy like the Milky Way with 100 billion stars, which is many billions of years old. But the James Webb Telescope has identified 6 galaxies that existed 500 million years after the Big Bang and are up to 10 times larger than the Milky Way. Now there is no turning back. The James Webb Telescope has discovered one of the oldest galaxies of all time, and it's so huge and luminous that it cannot possibly be a galaxy from the early universe. The U.S. physicist Michio Kaku suspects that we are now at the beginning of a new era and a new physics. This new physics could give more room to models such as string theory and the multiverse, and finally bring us the solution to the Hubble tension. Michio Kaku is right when he laughingly comments on the latest discoveries of the JWST. Webb showed us galaxies that supposedly existed in the early universe, but they are so large and so evolved that they must have been formed before the Big Bang. There has already been evidence in science that the universe as we imagine it does not completely match reality. You may have heard of the Hubble bias, a measurement inaccuracy in determining the rate of expansion of the universe. This problem has been known since the 1990s, and no one has been able to solve the puzzle. Now Webb relentlessly shows us that there are other things wrong with our cosmology and astrophysics. We may have been wrong on many levels. The Big Bang cannot possibly have taken place 13.8 billion years ago, if only 250 million years after it, there were already galaxies on the move in the cosmos, which, as Kaku points out, are larger than our Milky Way. According to our current understanding, galaxy evolution is a complex process that takes billions of years to produce galaxies like our Milky Way. Webb discovered dozens of these ancient, beautifully shaped, and large galaxies. Each one poses a puzzle to scientists, but not only that. Webb also showed us images of very large black holes that contained more than 1 billion solar masses just 500 million years after the supposed Big Bang. All these findings show us that our scientific understanding was wrong, and the launch of the James Webb Space Telescope triggered one of the biggest crises in modern cosmology. Michio Kaku laughs when he points out that some of the newly discovered galaxies appear up to 10 times larger than the Milky Way. The popular astrophysicist from the USA is one of the researchers who have long pointed out that our science has important gaps. His theories, which envisaged a unification of quantum field theories with the astrophysics of large phenomena, such as stars and galaxies, were not taken seriously in conservative scientific circles. It's precisely these conservative camps that now have a huge problem, because their rigid views of the cosmos and their ideas about the evolution of matter and the Big Bang are tottering. Instead, we will get a new physics, and thanks to Webb, we may discover completely new aspects of our universe. They really can't say that they didn't know anything because, in addition to the Hubble telescope, there were already a number of other indications before Webb that the old idea of the Big Bang and expansion cannot be entirely correct. Even the old Hubble Space Telescope discovered some suspicious points of light in the supposedly early universe. One of these discoveries was the galaxy known as GZ9P3. Hubble only recognized the galaxy as a very vague spot of light, which was undoubtedly there but did not allow any more precise analyses. Only Webb shed light on the darkness and took another look at GZ9P3. It turned out that this light was really emitted by a very old galaxy. Under Webb's sharp eyes, the galaxy showed a redshift of Z equals 9.3, which means nothing less than that we are looking at a galaxy that existed only 510 million years after the Big Bang. This means that GZ9P3 is also a primordial galaxy that is far more massive and mature than would be expected for its age. The galaxy also shows some anomalies that give researchers food for thought. It has a strange shape with 2 bright spots revealing its 2 dense cores. This suggests that we are actually looking at 2 galaxies, and that we are witnessing a galaxy merger in the supposedly early universe. Mergers of 2 primordial galaxies in the early universe would not be unusual, but even if we consider these 2 galaxies separately, they are too large and too evolved to be truly baby galaxies in a young cosmos. By our old standards, it takes billions of years for galaxies to reach this level of maturity, but we see the galaxy as it was 510 million years after the Big Bang. The galaxy is dominated by young bright stars, and researchers have found specific elements such as silicon, carbon, and iron that indicate older stars. These elements are not typical of the first stars, they only formed after many epochs of stellar evolution. This fact also speaks against us seeing a young galaxy here. As you can see, something cannot be right here, and scientists have not yet found the solution to the problem. The discovery of more old stars suggests that stars formed earlier and enriched the universe with metals faster. The old stars in GZ9P3 may also show that the galaxy matured chemically faster than thought, or we may have been wrong about the age of the universe, and this is where the Hubble tension comes back into play. Is expansion a lie? Did you know that the expansion of the universe has never been fully proven? The idea that the universe is expanding is a theory for which there was significant evidence, but problems with this theory soon emerged. Expansion is one of the cornerstones of our modern cosmology. In the 1920s, it was like a revolution, just as Webb is revolutionizing our view of the world today. Let us consider for a moment how this realization came about, what evidence supports it, and what contradictions or inconsistencies there are. The first indication of the expansion of the universe came from Vesto Melvin Slipher, an American astronomer who studied the spectral lines of galaxies in the 1910s and found that many of them exhibited a redshift. This indicated that these galaxies were moving away from us. However, the decisive breakthrough came in 1929 when Edwin Hubble, also an American astronomer, discovered the relationship between the distance of galaxies and their escape velocity. Edwin Hubble used the Doppler effect to measure the speeds of galaxies and found that more distant galaxies were moving away from us faster. This led to the formulation of Hubble's law, which states that the speed at which a galaxy moves away from us is proportional to its distance. For a long time, this law was regarded as the first clear proof that the universe is expanding. In addition to the redshifts, there is further evidence for the expansion of the universe. The cosmic microwave background, or CMB for short, is the background radiation of the universe dating back to when the universe was about 380,000 years old. It was discovered in 1965 by Arno Penzias and Robert Wilson. The uniform temperature distribution of this radiation in all directions indicates that the universe was once much denser and hotter and has been expanding ever since. Further evidence was the so-called Big Bang nucleosynthesis, which states that the abundance of light elements such as hydrogen and helium formed in the early universe is consistent with predictions of an expanding universe. Despite this evidence, there are also contradictions and unresolved questions about the idea of expansion. The most interesting of these is the Hubble tension. Hubble tension refers to a discrepancy between the values of the rate of expansion of the universe when different methods are applied. One method for determining the Hubble constant uses satellite observations of the CMB. The measurements were carried out with the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, among others. These measurements always result in a Hubble constant of about 67 to 68 km/s per megaparsec. Another method uses so-called standard candles, whose light provides fixed points for measuring distances and speeds in the universe. Scientists use Cepheids and Type Ia supernovae in particular as such standard candles. Cepheids are pulsating stars whose luminosity is related to their pulsation period. Type Ia supernovae have a standardized brightness. By measuring their apparent brightness, distances can be determined and combined with redshifts to calculate the expansion rate. This method yields a higher Hubble constant of about 73 to 74 km/s per megaparsec. Several explanations for this discrepancy have been proposed in the past. There could be a systematic error in the measurement methods or assumptions, and as a result, the results are distorted. Many researchers suspect a misunderstanding in the theories of dark matter and dark energy. Both are said to make up the vast majority of the universe, but we have not yet been able to measure or prove them, so we know very little about the true properties of either. Previously unknown aspects of dark matter and dark energy could explain the tensions. According to James Webb's current observations, scientists even suspect that dark matter and energy could change their properties, making them physically unmeasurable or undeterminable. If this is true, we are very unlikely to ever be able to scientifically describe the universe in its entirety. However, there are other explanations for Hubble's tension. The standard candles could be influenced by their respective surroundings, and thus not be reliable measurements after all. At the moment, it looks as if we are heading towards a new physics that will bring new insights and models. The expansion, or rather the drifting apart of certain areas of the universe, is certainly not a lie, but a clearly observed fact. However, it's currently unclear whether the entire universe is really expanding and whether it is drifting apart evenly. Observations of areas with a slower expansion and of phases with an increase in the rate of expansion rather suggest that we are in an overall dynamic structure. However, this does not necessarily have to have had a single starting point. Has Michio Kaku found the answer? Michio Kaku is one of the new scientists who see an opportunity in the current crisis. Kaku is known for his ability to make complex scientific concepts simple to understand, and he has long said that our old cosmology cannot be right. In Kaku's scientific work, the multiverse is the most likely scenario, or in other words, a cosmos in which many universes exist, and in some of these universes completely different physical forces can be at work. Kaku does not see the Big Bang as the definitive beginning of everything. If it really did exist, it was only the start of our universe, which is just one of many. Subscribe to the channel now and be part of every new video.